So basically, we'll be starting with why quantum computing. So obviously, right now we do have computers and they are classical. So what are the few drawbacks in them and what quantum computing brings new to the table? We'll look into this today. So basically, let's just look at how classical computing works because it in itself is really amazing. To achieve classical computing is awesome. So we all know that it depends on 0 and 1. That there can be two states, 0 and 1, on or off, and that is basically the flow of electricity. If electricity is flowing, it's on, and if it isn't, then it's off. And out of this, we get two states, 0 and 1. Now with 0 and 1 is something, everything our machine understands in 0 and 1. So like we have this ASCII system wherein we've given notations to all the characters and letters, numbers, etc. And like if A is 01001, so machine will understand if at the first position electricity is flowing or not. So everything is understood in 0 and 1. Even if you send an emoji to your friends, even that is encoded as 0 and 1. And even in a better way to understand the code that we write, whether it be C or Python, if we look at its object file, then it is 0 and 1. Over here, it's represented in hexadecimal, but that can easily be converted into binary. So basically, the complete classical computing system works on 0 and 1. And that works on and off, like I told you with the electricity example. Over here, there are just some analogies that when this water is not flowing, it's off, and when it's flowing, it's on. And how do we achieve this in our classical computers is through transistors. So basically, transistors made out of semiconductors allows the flow of electricity when we want it to and as we want it to. And I'm pretty sure we all know about this. So we know that computers are made out of integrated circuits, and integrated circuits are just different transistors put together. So basically, everything that we do is understood as a disco of electrons, if you want to imagine it like that. Basically, electricity flowing and not flowing in some places means different things to the computer and to us as humans. And because of that, we can write stuff in our Word documents, we can play video games, and everything that we do on our computers. So now what the problem is that since 1970 till now, every 18 months or approximately, if you want to say 2 years, the number of transistors in the same amount of given area doubles. So basically, if we talk about 1 centimeter square, then after 2 years, there will be double the number of transistors. So for the number of transistors to increase, obviously their size has to decrease. And this thing is called Moore's law. So the problem is that, so there are billions of transistors already in the size of a coin. So the typical size of an atom is 0.1 to 0.5 nanometers in diameter, and that of transistors is 10 to 20. So this is really close. If you look at the image, then the size of the man is that of the atom, and the size of the building is that of the transistors. So they are pretty comparable, like transistors have reached a very small size now. And the problem that occurs at this size is that classical computing works on the principle of 0 and 1 on or off. So that means if we don't want electricity to flow, we can stop it. But at this level, what happens is that instead of bouncing off the barrier, which stops the flow of electricity, the electron is able to flow through the barrier basically. So when we want electricity to not go beyond the point, when we want zero state, it won't be so, because now the electrons basically electricity is the flow of electrons, and now electrons can move past that barrier, and this is because of the size of the uh, transistor has reached a very small size, almost comparable to that of the atom and the electron. That makes this possible. Why? Because many of us know, if you don't, I'll give you a refresh about it, that at atomic level, the electrons exhibit a probabilistic cloud. Basically, you remember that in chemistry we did S, P, D, F, which were in different shapes, spherical, and one like the infinity sign. So that was the probability cloud. You cannot really tell where the electron is, and the electron can therefore pass through the barrier. So how is this a problem? Because now when we want zero state, we won't get zero state. When we want one state, we won't get that. So this, as the number of transistors will increase, we will reach the limit of classical computing. And I hope it hasn't been too overwhelming. So I hope this GIF will help. So this is what is happening at the atomic level. Basically, a person moving through a barrier. So why quantum computing? Because of two reasons. First, that this limitation that I told you, quantum computing solves it. And other thing is, it helps in quantum speed up and optimization. That is those problems which are very hard or have a lot of states and normal computers are not able to solve them that quickly. Like simple example from computer science, traveling salesman problem. So those problems and other problems we hitherto imagined that can never be solved can be solved slowly and steadily. A few problems are being solved, and as the field improves, things will be more solvable. So let's just go through some basics. So we know that electron is a particle, and that we all know double slit experiment as well. Basically, there is a source of electron, and then there's a strip with two cuts in it, and then we see where the electron lands on the screen. So over here, I have a question for you guys. If this electron passes through these slits, then we'll get something like situation A or situation B. What do you think? Electron is a particle, and if it is beamed on the first screen, then on the screen behind, what sort of pattern will we get, A or B?
A. I mean, if it's a particle, then A.
Okay, cool. So we think that it's only a particle, but it is actually not just a particle. So we get something like this. We throw one electron by one, following the other. So first we get dots here and there. Then as we throw more and more, the last picture shows us that we get something like what is shown in B over here. And we remember this from Young's double slit experiment. This is what happens in case of light. So where there are white pattern, that is constructive interference, and the dark area is destructive interference. Therefore, there are no particles over there. So we know that electrons are particles, but this proves that electrons are both particle and wave. So this is the pattern that we get. So initially there is no pattern, and then over a period of time we do realize that this is something like the light experiment only. So this proves that electron has wave nature as well. So therefore it means that there is wave particle duality. We know that light is also both wave and particle. We know it's a wave from Young's double slit experiment and a particle from photoelectric effect. That's not that important to know right now. But the point is that at microscopic levels, everything is a wave or a particle. And even at bigger levels, everything is a wave or a particle, but we are just not able to sense it that way, and we think that everything is particle. So this image is really cool because this image shows us a droplet as a particle as well, and these waves forming around it as well. So this is what an electron is like, both particle and wave. And because of the wave nature, we have that problem of tunneling as well, because of increasingly smaller sizes of transistors. So now over here, there's this new word, qubit. So qubit is basically, in classical computing, we have classical bit. In quantum computing, we have quantum bit, which is called qubit. So qubit can store multiple values simultaneously. Now, if you look at this image, in classical computing, we had two states, either 1 or 0, on or off. In quantum computing, we have one thing, basically a qubit can exist in multiple states at the same time. Means it can be 0, it can be 1, it can be any complex number in between. And this is because of its wave nature. Basically, the particle is in superposition because of wave nature. So yeah, it's 0, 1 and every other number. But when we measure it, it collapses to one of the states, 0 or 1. Something like this. This is a coin. When it's tossed, you can't tell in which state is it, that it's in heads or if it's in tails, because it's in both at the same time. But when it stops, when it collapses, it's either heads or tails, so it's either 0 or 1. So because of superposition, the qubit can be in any state, and when we measure it, it takes one of the states. And qubits are physical systems. Classical bits do not exist. It's just flow of electricity. Qubits can be anything like spin of an electron and many more things. So this falls under quantum hardware, and there is a lot of work going on in it, and there are different types of qubits, but majorly they are physical entities that exist at microscopic level. We'll look into them later. Now, one important thing is the bracket notation. You can look over here that this looks like a weird expression. So what does this mean? And you can see there's this horizontal line, then an angular line, and in between there is 0 or 1. So that is called a ket. And bra is opposite of it. The angular line comes first and then the horizontal line. So we'll look into it over here. Yeah, so this is the same thing, that classical bits are deterministic, that is, it can be 0 or 1, and quantum bits are probabilistic, that it can be both 0 and 1 at the same time with different proportions of it. And when we measure, then they'll be either 0 or 1. So you could basically say that classical bits are a special case of quantum bits. So this is a bit of notation. This notation is called Dirac notation. So basically this is a ket. So this is the wave function, that is A0 ket and B1 ket. Basically this means that the quantum state qubit can be 0 and 1 and anything in between, right? So this is a linear function just representing the same. If this psi function, this is called psi, this symbol, if it's in 0 state, then A will be 1 and B will be 0. And if it's in 1 will be, for B will be 1 and A will be 0. And if it's in somewhere between, then A and B can take up different values. So a 0 ket basically means that probability of measuring and observing the value of qubit to be 0 is 100%. So it's written like a row matrix. Sorry, that's a column matrix. And the first number 1 over here means is that it's 0, and 0 over here is 1. Basically, this is A and B. So therefore, A is equal to 1 over here. And 1 ket means the probability of the state being as 1. So over here, we have 1 over here and not over like 0 ket. So this is the equation that we had. A ket 0 plus B ket 1, and if we open these kets into the column matrix form, then if we then multiply A and B and then we add it, we get this, that the probability of the state of the qubit being 0 is A and of being 1 is B. So then when we A and B are complex numbers, and when we measure the probability, then it's not just A, it's A square and B square, because complex numbers, the probability won't add up to 1. So therefore we square them, then the rule of probability of all the probabilities of an event being 1 holds. Otherwise it won't hold. So this is the basic way how we represent our qubits and different states. So till now, basically, we're close to the end now. So basically, these are the three quantum mechanics concepts that affect quantum computing and have enabled quantum computing in the first place. So superposition is what we saw, that when we toss the coin, it can be both heads and tails, and when it collapses, it is one of the states. So superposition is the main idea because of which a qubit exists, basically in a superimposed state of both 0 and 1. Then interference is like that double slit experiment that we saw, that we get constructive interference at some places and destructive interference in other places. And this is really helpful how when we have bigger problems to solve, so what interference does is that those answers or states that are more likely to solve the problem are constructively interfered, and those that are not the answers are destructively interfered. So basically those options die, and we're left with lesser number of options, lesser number of states that can possibly be our answer. So basically interference leads to quantum speed up. How are we able to speed up the solution? How are we able to speed up the way of getting a solution for the problem is by eliminating those states using destructive interference that cannot be the answer. So then we're left with a lesser number of states. And entanglement is something we'll come up to later on. So basically, this is what I explained, quantum speed up, that one of the reasons of quantum speed up is interference. The other is the possibility of a qubit to store a lot of states. I'll show you over here. So in classical computing, we have 0 or 1 as the possible permutation. But if we have two qubits, they can be anything when they collapse. So we get these four options, 0, 0, 0, 1, 1, 0, 1, 1. So if there are two classical bits, then they will hold two states. But if we have two qubits, then they are able to hold four states. So the generalized formula is 2 to the power n. So if we have 3 qubits basically, so that is equivalent to 8 classical bits. So what 8 classical bits will store can be stored in just 3 qubits. Likewise, we see how quickly these numbers increase, and in just 300 qubits, we can store exponentially such a huge number of states. So if you're able to hold so many states in just 300 qubits, then obviously we are able to compute more number of states. Therefore, we are able to solve those problems that require a lot of states and were not solvable till now. So this is like an analogy for it. If you send a child in a room to find something, so that child will look in a drawer, look in the almirah, look under the bed. So a lot of like, for supposedly the thing is under the bed, and the child first looks in the drawer, then the almirah, then under the bed, and let's say every task take him 1 second. So total this child took 3 seconds. Now we send three children in the room, and all of them simultaneously looked. One looked in the drawer, one looked in the almirah, and one looked under the bed, and they found it in 1 second because there were more states. So basically, this is how there is quantum speed up because of the states. And then entanglement is a really cool concept that allows us for us to have a lot of applications. Like if there are these two t-shirts and you and your brother are entangled since birth, of course, and you are at a distance right now. He's in his college, you are in your college, and you're far away. But entanglement is like if I choose to buy the black t shirt, then by default, my brother will buy the pink one. That is entanglement. Like if there are two qubits, both are in superposition right now, and if my qubit collapses to the state of zero, then I already know, even without my brother's qubit collapsing, I know that his qubit will end up to be 1. So this is really amazing because this is the flow of information over a very large distance without us even measuring the other person's qubit. Something like this. If you had two qubits, two entangled photons, you separated them, gave it to Alice and Bob. They went far away. Then Alice chooses to measure her part and finds it to be A. Then Bob will automatically have a correlated answer. So that is what is entanglement. And together, these three processes of interference, superposition, and entanglement are the ones that allow for us to do what we can do in quantum computing.